It's right here. We started talking about operational amplifiers, and I summarized the different configurations in which op amps can be connected. Okay. Basically, it's a 3-terminal device. What it does is to amplify the difference. Okay.
Professor?
To amplify. Yes.
I can't see anything on the screen.
Sorry about that. Let me see screen. How about now?
Yes.
Okay. Let me see. I'm gonna have to do that. Okay, so we started looking at the operational amplifiers, and I summarized op amp in 3 or 4 pages. Basically, it's a 3-terminal device if you exclude the power supplies. What it does is to amplify the difference between V input positive and V input negative. The difference between these two terminals is multiplied by what is known as open loop gain A. Okay, this A that's supposed to be a really, really large number is called open loop gain. Okay, it's called open loop gain. Now I mentioned there are limits, the maximum and minimum output value that are possible out of the V out of an op amp are really set by the power supply plus VCC and negative VCC. Okay, we discussed about that in this last class, the previous classes. Then I gave you a couple of rules. that you apply over and over again when you're solving problems with op amps. The first one is called a virtual short. Okay, the idea of virtual short is very, very simple. Whatever voltage is applied on one terminal automatically shows up on the other. Okay, if one of these voltages, doesn't matter which one, if one of these voltages is 10 volts, the other terminal also tracks 10 volts voltage. Okay, if one of these voltages is, I don't know, if one of these two terminals is 3.14 volts pi, the other is also going to be 3.14 volts. One is going to track the other as if they're shorted together, as if they're tied together. In reality, they're not tied, but they behave exactly as if they are tied together. They're shorted together. That's the idea of virtual short. Okay. Now, if one of these terminals is tied to ground, the other also behaves like it is tied to a ground. It's just a virtual ground. Okay. So that's the idea of virtual short. This happens because the open loop gain tends to be a really large number, close to tens of kilo ohms. Okay, hundreds of, not ohms, tens of kilo, 10 to the 5, 10 to the 4, hundreds kilos, so on and so forth, 100,000. Okay, that kind of large numbers. Okay, they necessitate that the input voltage difference be extremely small. The output voltage has to be finite. Okay, then we looked at the 3 regions of operation: positive saturation region, negative saturation region, and linear region. Linear region is where we like to operate. Then we talked about the different kinds of op amp configurations. Inverting amplifier, where the input is applied on the negative terminal. And the V output is V source times negative RF over RF. Then I talked about non-inverting amplifier, okay, where V input is connected to the positive terminal. Output voltage is the input multiplied by some positive gain, 1 plus RF over RF. Okay. Then we talked about the difference amplifier or inverted summing amplifier, isn't it? This is the inverting summing amplifier. There are three different input voltages scaled and applied to the negative terminal, VA, VB, and VC. They're all applied to the negative terminal. Once they're applied to the negative terminal, the final overall output is VA scaled by some negative weight, VB scaled by some negative weight, and VC multiplied by some negative weight. They're all added together, hence the name weighted summing amplifier. Okay, and then I gave you techniques, the general procedure to solve the problem, op-amp problems. Okay, let's see if we can, where did we go? The generic approach when you're solving op-amp problems is to start with KCL at Vn, because your negative feedback is at the Vn terminal. You begin by writing KCL at the Vn node. The step 2 is to apply the different rules, rule number 1 and 2. Okay, so let's see if we can do this in action, if we can look at this in action one more time. We did some problems. We did a bunch of problems actually on how to solve these circuits. Okay, and then I showed you how the results are obtained. The results that I discussed are obtained. Okay, here is an example problem we did. Okay, what we want to remember is, let's see, there is VA, okay, there's VB, and there's VC. If you look at VA and VB, okay, if you look at VA and VB, both of these are applied to the negative terminal. VC and VD are applied to the positive terminal. And for if you evaluate this, you see that the VC and VD are multiplied by some positive coefficients, and VA and VB will be multiplied by some negative coefficients. Okay, so that's the problems that we saw in the last class. Let's see if we can continue here. I want to spend a whole lot of time doing, or at least a little bit of time doing op-amp problems, and then maybe leave chapter number 6, only cover chapter number 6 in a very quick manner, because it's inductance and capacitance, concepts in some respect that are similar to resistors when it comes to parallel and series connections. We'll talk about that. So if you're comfortable doing series and parallel connection of resistances, you should pick up the idea behind series and parallel connection of inductances and capacitances rather quickly. On top of that, inductance and capacitance also have the ability to store energy, which is lacking in resistances. So we'll talk about the big differences and then try to spend a little less time on similarities. Okay, but I do really want to spend some time on the op-amp problems. That way we can get more practice. Okay, so let me give you another problem and see if we can spend some time on an example op-amp problem. 2. We already looked at one problem. Let's see the other problem. The problem is there is an op amp. There's an op amp, okay, with its negative terminal and its positive terminal, okay. On the negative terminal, this guy is down, this guy is applied, a voltage is applied. Let's see, plus or minus 5 volts is applied, okay. That's the ground. And then this guy, okay, the positive terminal is tied to two resistors, 3 kilo ohms and 6 kilo ohms. And then a positive signal is applied, 3 volts. Okay, here is the output. Okay, the output is tied to a 4 kilo ohm resistance. 4 kilo ohm resistance. This voltage is V, output V of. There's a feedback that goes like so. Okay, let's see, the feedback resistance is 5 kilo ohms. Okay, so the question is, we are supposed to find this guy, the current I flowing through the load resistance. This guy is called the load resistance, IL. What's the value of IL is the question.
Hey, Professor.
Yes.
The leftmost resistor hasn't been given its value yet.
Thank you. Okay. All right. How would we go about solving this problem? Where do you want to begin?
I would start at the node Vn.
Okay. First, let me annotate Vn then. That's going to be Vn. That's Vp. So let me write that down. This guy is Vn. This guy is Vp. Okay. So let's begin at Vn. Okay. So let's write KCL at Vn. Okay. Okay. So let's write KCL at Vn. What are the different currents in there at that node?
So if we go to the left, you would have the voltage Vn minus 5 volts over 10 kilo ohms.
Yes.
And then if we go in the upper branch, you would have Vn minus V naught over 5 kilo ohms.
Yes.
And then the last current to the right is the inverting input current, which we know will go to 0.
Thank you. It's the current going into the inverting input. All of that is 0. And then when we apply the rules, we know for a fact that this guy is going to go to 0. Okay. So now I have this guy. The resultant equation is Vn minus 5 volts by 10 kilo ohms plus Vn minus V0 by 5 kilo ohms. All of that equals to 0. So I leave it there. That's step 1. Step Okay, let's look at step number 2. Okay, because we don't know the value for Vn. So we know if we know the value for Vn, okay, if we knew the value for Vn, we would plug that in, okay, we would plug the value for Vn and get the value for V out. Once we find V out over this resistance, 4 kilo ohms, should give me the value for IL. That's my strategy, right? So in order for me to be able to find IL, I want to find out V naught. Once I have V naught, I simply divide it by the resistance to get a value for IL. So the point is, at step 1, if I knew the value for Vn, then finding out V naught is simply a matter of algebra manipulation. So how do you think we can find Vn?
You would use the infinite input resistance rule.
Yes, yes, which states that Vn would be Vp. So if I can find the value of Vp, then that's exactly the same as Vn. So how do we know Vp? So the problem comes down to finding the value for Vp. How do we find Vp?
You could use voltage division to find VP.
Yes, I'm going to use voltage division to find Vp, because if you think about it, this current here going into the op-amp is 0. There's absolutely no current going into the op-amp. So it's almost like, it's exactly, as a matter of fact, like I'm applying a 3 volts voltage source through a 6 kilo ohm resistance and a 3 kilo ohm resistance. This connection to the right is as good as not being present, because the current going in is really 0. Okay, so once I know that this connection is only there for voltage sake, the current is not really present. So in order to find Vp, I use a voltage division. That's going to be 3 kilo ohms divided by 3K plus 6K ohms times the voltage applied, which is 3 volts. So this comes out to be 1 volt. So I know for a fact that Vp is 1 volt. Once Vp is 1 volt, I know the value of Vn. Once I know the value of Vn to be 1 volt, I can plug that in to this first equation. Let me call this equation number 1. Okay, I'll call this equation number 1 and get a value for V out. Okay, what would be the value for VO? If you plug in a value of Vn equals to 1 volt into the above equation, into the equation 1, what do you think is the value for VO?
-1 volt.
-1 is correct. -1 is correct. Once you have VO, you should be able to find IL, which is -1 volt over 4 kilo ohms. So how much ever that comes out to be negative. So IL is negative 250 microamperes. Okay, negative 250 microamperes is the result we were after. Questions about that, please? And as you can see, I did not do anything in this problem. You, gentle ladies, drove the discussion, both of you. You drove the discussion forward, and I appreciate that. Okay? Questions, please. Okay, let's see if we can do one more problem. Let's see if we can do one more problem. The next problem is going to be more simpler, okay, compared to the first problem, very first problem that we did. Okay, the reason is I wanted to begin with the most daunting looking, uncomfortable looking kind of problem in the beginning. Okay, so in this problem, example problem number 3, let's see. Okay, there is the positive terminal on the top. There's a negative terminal on the bottom. The positive terminal is connected to a positive power supply. Is it connected to a positive signal? A signal, okay, of 2 volts. Okay, let's see. Now, the output is over there. Okay, that's V output. Okay, and this is what we are supposed to find out. The problem is find out the value for V out, given that the negative terminal is connected in this fashion. Okay, let's see. Okay, and there's another resistance over here, 10 kilo ohms, 20 kilo ohms. Okay, what else? Did I give you everything you need? Yes. So now then, how would you go about solving this problem? Okay, it's still go ahead.
Oh, sorry. Oh, we start with rule 1, the virtual short.
Okay, so virtual short. So whatever voltage is on the positive terminal
Will be the
shows up
same
on the
the
negative terminal. Yes, so this is going to be 2 volts as well. Right? So meaning that this voltage right at this node, which I'm going to call as Vn, that's going to be 2 volts as well. Okay, so step 1 is the idea of virtual short, which gives me that Vn is the exact same as Vp, which is what we applied to be 2 volts. Very good. How about step 2? What would be the next step? KCL at node Vn, that guy right there, this guy is Vn, right? So we can apply KCL at Vn, and that's exactly what we had been doing all along. In all the example problems, in the different configurations, all the problems, we have been doing the exact same thing. Okay, if you think about it, this appears like a different problem, but it really is not. If you think about it, I'm going to modify this, not really modifying it, but redraw this without actually modifying it. That's a right way to say it. So this guy, it's on the same node still. Okay, so what is going on here is there is a feedback resistance RF through which the output is tied back into the negative terminal. Then there is RA, okay, which is connected to ground. So it is still an inverting amplifier configuration, okay, through RF, the feedback resistance, tying it back to the negative input terminal. So it really is nothing different from the configuration that we already know, okay? So let me go back to the way the circuit has been shown, okay? So once we apply step 2, so the procedure is still going to be the same, applying KCL at node Vn, okay? At node Vn, if you look at the currents that are leaving the branch, there is one current going left, which is IN. There is one current going down. There's one current going up. Okay, could somebody help me set up these equations?
Yes. So this is how I would set it up. It would be Vn over 10 kilo ohms
That's the current going down.
plus In, which will be 0,
Yes.
plus Vn minus V naught over 20 kilo ohms is equal to 0.
Thank you. Like you mentioned, IN is going to be 0. Okay. Now, once we have this Vn over 10 kilo ohms plus Vn minus V naught over 20 kilo ohms equals to 0. But we do know from above that this guy, Vn, is 2 volts. Right? We know for a fact that Vn is 2 volts. Okay, so once we plug in Vn equals to 2 volts, which we got from the step 1, okay, gives us a value for V naught, and that is what we are after. Okay, what value do you get for V out? V naught, VO.
I got -2.
Negative 2 volts. Let's see.
Or did I mess up the?
You should see something around.
Vn is 2.
Vn is 2 volts, right? We can double check. We can double check. One of us is definitely correct. So we can come back and double check that. But you know what to do from here. Plug the numbers in and then get the value for VO. Okay. Now, questions so far, please. So this will be the last problem I want to solve on op amps. Don't be intimidated. Don't be deterred when you see a problem or a circuit that you have not seen before, because the underlying steps that you want to take, the steps that you want to follow, are still very, very, very identical. As a matter of fact, apply the 2 rules, virtual short and input current is 0. and then apply the KCL at Vn. Okay, so there's no rocket science here. It's just if you're not able to solve any problem in op amp, let me tell you, that's because of an inhibition you have in your mind. I know for a fact that I have given you all the tool sets, all the tools necessary to solve any op amp problem that you will encounter on the homework or on the exam. So if for some reason you find yourself in a situation where you don't, you're not able to solve it, I would turn around and say, well, that inhibition is in your head. There's only two steps that you have to do. Apply the KCL and apply the two rules. That's all there is to it. Be strategic, and then take a step back, look at the big picture, and then strategize on how you want to unravel the problem. Questions, please. Okay. So that's about op amp. We did a bunch of problems. We did 3 problems actually. To begin with, on Friday, okay, that is when I wanted to tackle the most intricate looking op amp problem with 2 inputs on the positive and 2 inputs on the negative and a feedback. Once we did that, the other problems look like a piece of cake. Okay. All right, so let's move on. So that's about as much time as we want to spend on the op amp chapter. Okay, I know a couple of you sent me emails over the weekend. In general, I had been able to respond to your emails within a reasonable time frame, and I will continue to do that. It's just that I did not get a chance to respond to your emails. I will respond to them by the end of the day today, or first thing in the morning tomorrow. Okay, a couple of you sent me emails. All right, so let's look at this inductance and capacitance. But before we do that, let's see where we are doing with where we are with the syllabus. Right. So today is the, right, let's see, today is the 3rd. Oh, tomorrow is the exam, right? Of course. So we want to finish inductance, capacitance, series parallel connection of inductance and capacitance. Okay, let's see if we can quickly spend some time on that. All right, what is inductance and capacitance? Earlier, I mentioned that electricity, when there is a charge, okay, when there is a charge, separation of charge manifests as voltage, and movement of charge manifests as current. So all of electricity, electronics, is just artifact, okay, of charge. When charge is moving, that leads to current. When charges are separated, that leads to potential difference or voltage. Okay, so we're going to look at a different manifestation of charge now. So when charge is separated, okay, that leads to an idea of what is known as capacitance. Okay, separation of charges leads to capacitance. Okay, the idea of capacitance. Also, we saw earlier that movement of charges leads to current, which is also used more. The concept also underlies the idea of inductance. Okay, inductance. We'll talk about this shortly. Okay. Now, let's start with inductor. What is an inductor? Here is the symbol for inductor. A coil, a winding coil is a symbol for inductor. Okay. A resistance is peak and valley, that kind of symbol. So here, inductance is a coil. Because underlying physically, inductances are made out of long wires that are wound around themselves. Okay, so the symbol, the letter symbol, alphabet L, is used in representing an inductance, and then it is a consequence of a conductor, a long conductor that's carrying current. Okay, and that mechanism is linked to the magnetic field. For us, for our analysis, what we want to understand is the amount of current flowing in a conductor, in an inductor. Okay, I sets up a voltage. So the voltage across the inductance is proportional to the rate of change of current. Okay, earlier V of a resistance was proportional to the current, right? And this R is the constant of proportionality. Here, the voltage across an inductance is not proportional to I, but it is proportional to di over dt, and L is simply a constant of proportionality, inductance of the inductor. Okay, we can rearrange this. We can rearrange I to be 1 over L integral 0, t0 to t, VL of dt plus some initial condition. Okay, what's the current that's at time t equals to 0? So using calculus equations, we should be able to rearrange in terms of VL and in terms of IL. Okay, now we use the voltage across an inductor in accordance with the passive sign convention. Okay, passive sign convention, something that we have, the very first tool set that we looked at. Okay, passive sign convention. Then the units of inductance are Henry. Okay, units of inductance are Henry. Typically, it's a really, really large number. It's a really, really large unit. So practical inductances have values in the range of millihenry. Okay, millihenry is a more practical number. Now, so the relationship between the voltage and current in an inductance is different from that in a resistance. Okay, it's the slope of a constant current in constant change in current that creates a constant voltage across an inductance. So earlier I mentioned that V of a resistance was proportional to I of a resistance. However, the V of an inductance is proportional not to I, but the rate of change of current. So if the rate of change of current is 0, or in other words, if a constant current is flowing, if I is constant, okay, what do you think would be the voltage across the inductance, VL?
It would be 0.
It would be 0 because that's the slope, that's the rate of change, right? So the rate of change of current is 0 when it is constant. So when the DC current, when a DC current is applied to an inductance, okay, the voltage across such inductance is 0. Okay, so that's the idea.
So then you would need an AC current?
Yes. Yes.
Okay.
To set up some voltage across inductance terminals, we need an AC current. Okay. Now, so when a constant DC current is applied to an inductance, okay, it acts as a shock, meaning that there is no voltage drop across these terminals. It acts as a short circuit to DC. Okay, when a constant DC is applied, there is no voltage drop. So this is V I of an inductance versus V of an inductance, IV graph. Okay, when a constant DC is applied, inductance acts as short. Okay, so that's one of the rules that you want to remember. And you know where that rule is coming from the fact that the voltage of an inductance is proportional to the slope of the current or the derivative of the current. Okay, now inductances have the ability to store power, to store energy in the form of magnetic field. Okay, the amount of energy stored in an inductance is 1/2 Li squared. Okay, so this is a very familiar form. It's close. This is a very familiar form. 1/2 mv squared is the energy, kinetic energy of a moving body with mass m and velocity v. We know that energy typically takes this form, 1/2 kx squared. Does anybody recollect what energy that represents?
Is that Hooke's law, the energy in a spring?
Yes. Okay, the energy stored in a spring, okay, is k times x squared, where x is the amount of compression distance and k is the spring constant. So the idea is that this form is familiar to us. So the energy stored in an inductance is 1/2 Li squared. So when we go further and see the capacitance, the energy stored in a capacitance would be 1/2 CV squared. Okay, the energy stored in an inductance is 1/2 Li squared. Okay, so that's the idea. Now, let's see. That's the idea of an inductance. Let's see what's going on with the capacitance. Okay, capacitance is pretty similar to the inductance in the sense that one of the variables is proportional to the derivative of the other. Okay, in case of an inductance, the voltage of an inductance was proportional to the derivative of the current, time derivative of the current. On the other hand, this guy, the current of an inductance is proportional to the time derivative of the voltage of a capacitance. That's the idea. Okay, so that's the idea. Now, let's see. So this symbol capacitance, if you think about it, this is a parallel plate capacitance. Okay, two parallel plates that are charges that are separated leads to capacitance. Okay, that's all there is to it. So charges that are positive and negative charges separated, separation of charges leads to electric field in between these two charges. When charges are separated by an insulator, that leads to capacitance. Okay, there is no current actually flowing through these two terminals. Okay, but then there is a displacement current around the terminals of the capacitance. Okay, that it can be viewed pretty similar to current actually flowing through the incense, flowing through the capacitance. Okay, charge separation is due to displacement current. Okay, it's due to displacement current. Okay, now the unit of capacitance is typically farad. And like I mentioned earlier with inductances, the idea of farad is a really, really large unit. So practical capacitances are typically in the range of nanofarads to some millifarads, or in some cases farads. But typically, you'll see that, and in some circuits where you're dealing with integrated components, okay, it's not unusual to see picofarad quantity capacitances as well. Okay, you might even, farad is also a reasonable size for a capacitance, 1 farad, but it's not too often that you encounter this in electronic components, electronic circuits. Okay, so we still follow and apply the passive sign convention. We still apply the passive sign convention that when the current is aligned with the voltage drop, then the current is positive. Okay, if the current is opposite to the voltage drop, then such current is negative. Okay, this passive sign convention still applies in the case of a capacitance. So capacitance is nothing but separation of charges. Okay, so the capacitor acts as the opposite twin, the dual of an inductance. Okay, it's the slope of the constant change of voltage. So if you were to plot the voltage versus the current of a capacitance, okay, the current that is set up in a capacitance is really, let's see, let me do this guy, okay. Let's say I have a constant slope. This slope, okay, dVc by dt times some constant c gives me the constant current, okay. So in other words, for a capacitance to have a non-zero current, I have to have some kind of change in voltage, okay. Oops, that's not what I wanted to do. Duplicate that and do this, okay. If the voltage is not changing, if the voltage is constant like so, if the voltage is constant Vc, then the current, which is the slope of this guy, is 0. Okay, so in other words, the constant DC voltage implies the current flowing through the capacitance is 0. So when I apply a constant DC voltage across the terminals of the capacitance, the current around the terminals of the capacitance, or the current in the capacitance, is 0. Or in other words, capacitance acts as open circuit to DC. Okay, earlier I gave you a rule that said inductance acts as short circuit to DC currents. Okay, when there's a constant DC current through an inductance, then the voltage drop is really 0. Okay, similarly, I mentioned, remember, capacitance is the opposite twin, evil twin of the inductance. Okay, so in that sense, capacitance acts as an open circuit to constant DC voltage. And the DC voltage, when the voltage is constant DC, the amount of current set up in the capacitance is really 0. Make sense? Okay. Like I mentioned, the energy stored in a capacitance is, so this ability is not present in a resistance. A resistance cannot store any energy, right? Now, capacitance, on the other hand, can store the energy, okay, in the form of electric field, okay? That amount of energy stored is given by half CV squared. If you remember the inductance, it was given by half Li squared, the energy stored in an inductance, okay? But the energy stored in a capacitance is 1/2 CV squared, okay? Let's see, simple concepts, very interesting ideas, very simple concepts. But then when you move on to engineering EEE 117, okay, EEE 108, okay, all of these additional courses, or if you are to design any kind of electronic components, capacitors, inductance, resistors are the building blocks. Okay, so that's the idea. The bottom line that you want to remember is capacitance acts as an open circuit to DC, and then really IC is C dV by dt. IL is, or VL is L di by dt. Okay, these two equations similar to V equals to IR equation. So let me write them down because I have written in so many different places here. I just want to write one summary page. Okay, let's see. V is IR for a resistor. Okay, let's see. For an inductance, V is L di by dt. For a cap, okay, for a capacitance, I is C dV by dV dt. Okay, so now energy stored in an inductance is 1/2 Li squared. Okay, the energy stored in a capacitance is half C V squared. Okay, similarly, inductance acts as short circuit to DC currents, meaning that if the change in current is zero, implies the change in voltage or the voltage set up across an inductance is really zero. Okay, so this is inductor. Here is capacitor. Okay, capacitor. Now, capacitor acts as an open circuit to DC current. DC, is that correct? Capacitance acts as an open circuit to DC voltage, meaning that if the change in voltage is zero, then the current set up in a capacitance is really zero. Questions, please. What questions do you have so far? Okay. All right. So that's the idea of capacitors. Now let's move on and see how we can connect capacitors in the series and parallel. Okay. So the next idea is series and parallel combination of inductance and capacitance. So in one sentence, in 1 minute, I'm going to give you the gist. Okay. Resistance in series. Okay. Resistors in series are equivalent, equals to the sum of individual resistances. Okay. This is R1. We know this very well. That's exactly the case with inductances in series. Okay. Inductances, when they're connected in series, their equivalent inductance adds. So L1, L2, L3. So the overall inductance L equivalence is the sum of individual inductances. Simple idea. Okay. So now let's take a look at parallel connection of resistors. So when I have a bunch of resistors connected in parallel, okay, and I have 3 resistances connected in parallel, R1, R2, and R3, the equivalent resistance is, let me put it right here, 1 over, is dictated by this relationship, 1 over R1 plus 1 over R2 plus 1 over R3. Okay, the sum of the reciprocals of individual resistances. Exact same thing with inductances as well. Okay, when I have 3 inductances in parallel, or any number of inductances in parallel, okay, the overall inductance is going to be the inverse sum. So this is L1, here is L2, L3, okay? L equivalent is 1 over L1 plus 1 over L2 plus 1 over L3, okay? That's the idea of inductances in parallel, okay? They behave exactly like resistances in parallel. When it comes to capacitances in series, well, like I mentioned, it's the opposite twin sister, the evil twin of the inductance, right? So if I have C1, C2, and C3 in series, the equivalent capacitance, C equivalent, behaves similar to resistances or inductances in parallel. So C1 plus 1 over C2 plus 1 over C3. Pretty good. Okay. Similarly, when you have capacitances in parallel, when you have capacitances C1, C2, and C3 in parallel, the equivalent capacitance CEQ is the sum. Okay, it's simply the sum of different capacitances. Okay, so that's the idea of capacitances in series and parallel. Okay, very simple idea, something that you may have already seen in your physics course or your high school courses. Okay, but it's just a recap here. Questions so far, please. Okay, series and parallel combination of inductance and capacitances. Let's see. So, and they're going to prove this in any which way, in any number of different ways, by seeing the individual voltages here, by adding them up. The overall voltage is the sum of different voltages. So there is proof, really simple idea. There is proof here that the equivalent of three inductances in series is simply their sum, series combination of inductors. Okay. Similarly, when you look at inductances in parallel, their equivalent resistance is the reciprocal of the inverse sum of each of these inductances. Okay, we saw this already. And then of course, there are some simple problems, and I want to leave these problems as exercise for you. Current is given, okay, and at time t0, and current at I2 current in each of these branches, I1 and I2 current in branches are given. You're asked to find the equivalent inductance first. In order to find the equivalent inductance, you simply apply the parallel formula, because the inductances are in parallel here. Their equivalent inductance is 1 over L1 plus 1 over L2 whole inverse. So it's a simple problem. What is the initial current and its reference direction in the equivalent inductance? So you're going to apply the initial condition of 3 amperes that is given to be I1 at T0, and it's easy to find the current. Okay, so it's just a matter of V is L di by dt, or I is integral of V dt. Okay, so it's shown here. I leave that as an exercise for you. Okay, then the same with capacitances as well. What happens when capacitances are connected in parallel or in series? When capacitances are connected in series, their equivalent resistance is the inverse sum of the reciprocals of their capacitances. Inverse of the sum of reciprocals of their capacitances. Okay, and when they're connected in parallel, their capacitances simply add. Okay, and then there is a problem. V is given, I is given, an expression for I is given, and the initial condition for V is given to be negative 10 volts. You're asked to find the equivalent capacitance, and then of course the initial voltage across the capacitance, so on and so forth. Okay, initial voltage across the equivalent capacitance. Okay, so you can do that, and then once I is given, you should be able to calculate V by doing an integral 1 over C I dt. Okay. So that's all there is to inductances and capacitances. Okay. So like I mentioned, the big picture is, let's see. Okay. it's captured in this slide here that the inductance is LDI by dt. When there are series, you just want to add to this by saying that series inductance behave similar to series resistances. Series capacitances behave similar to parallel resistances when it comes to their equivalent value. Make sense?
Yes.
Okay. Let's see if we can stop there. Just give me a second.